So hi students, welcome to lecture 3. So we were dealing with high velocity forming, and from the previous lectures we have seen in the first lecture we have seen what this high velocity forming process is and how it is different from the normal conventional forming methods. Now after that we have seen the main two different types of forming processes which are used in industrial applications. One is your explosive forming and the other one was electro-hydraulic forming. Now, uh, so you might have got an idea about this high velocity forming process. Okay, right. So what is the basic process and what are the basic types? Now we'll be going in detail. Now how is this happening, or how this deformation is happening? Only thing is we are adding a high velocity or we are increasing the energy, that's it. So what is the effect that this addition of this velocity or increasing this velocity, what does it do, or how does this deformation is how is this deformation created in the metal? Okay, so we'll see that in detail. So what is the basic underlying principle in high velocity forming? Okay, so let us start with the effect of this high speed on metal deformation. Okay, this is a general heading, that is, how does this high speed affect the metal deformation? Now before going to this, you should the you should know that the desirable property, the best desirable property for a metal for to form are that it should have a lower yielding point and it should have a higher ductility, right? Because you are actually drawing, or whatever it is, while forming you are actually changing the shape, right? So the metal should be ductile. First of all, the first important thing is it should be ductile, and the yield stress should be lower so that it can move to the plastic limit. Okay, so this is the best desirable property. At the same time, the material should have high strength as well, right? Now, how is this achieved in high speed, or when the velocity is increased? Okay, so the effect of high speed on metal deformation has been investigated from two main points of view. Okay, the first point of view is the effect of this high speed or the high velocity on the stress strain curve, that is, on the material behavior, right? So first of all, we'll be analyzing the effect of the high velocity on the strength of material, or the effect of strain rate on the stress strain curve. Okay, so the strain rate, I think it is a new term for you. Strain rate actually means it is strain with respect to time, right? The strain happening with respect to time. Now, when you compare it with conventional forming methods, you can see that uh, strain rate is higher for high velocity form. Since the velocity is higher, when the velocity is higher, the strain produced or the strain induced in the material is higher, because the forming is happening in a quicker way, right? Therefore there is a high strain rate occurring in high velocity forming, right? So we'll be first of all investigating the effect of this high strain rate, or the effect of this strain rate on the stress strain curve. Now after this, we'll also analyze the propagation of stress waves in deformation of material. Okay, so we'll be dealing with the concept of stress waves as well, right? So we have seen in explosion forming and high electrohydraulic forming that after the explosion a high intensity wave is produced, and this wave is actually producing the deformation. So the second important topic is to understand this concept, what is happening over there. Correct. Now let us start our journey, or let us start our discussion with the effect of high speed on stress strain relationship. Fine. Now for high velocity forming, your strain rate will be very high, as we have just discussed this one, right? When the velocity increases, the strain produced, the rate at which the strain is produced also increases, and therefore it will be having, obviously it will be having a high, the strain rate will be very high, right? Now, so what are the effect of having a high strain rate during forming? Okay, it is actually this is a very interesting, as well as it is actually a high research topic, and going in depth is not it is beyond the scope of this as far as your paper is concerned. Okay, if you can search this one in Google and all, you can find a number of papers related to the high strain rate and the effect of this high strain rate on the material behavior, right? Okay, so as a summary of all those things, we'll deal we'll take the summary of some of those aspects. Okay, so the effect of high, so what is the effect of this high strain rate on forming? Okay, so the direct effect is the around flow stress. Okay, flow stress is nothing but the instantaneous value of stress required to continue the deforming the material. Okay, so flow stress, as the name suggests, flowing stress, right? It is actually the stress required to sustain the flow, or the stress required to make continue the deformation process. Okay, so the flow stress increases with the strain rate. So when the strain rate increases, the flow stress also increases, thereby helping this forming process, right? Okay, another important thing, effect of this high strain rate is that the temperature of work increases due to adiabatic heating. The temperature of the work also increases, flow stress increases, as well as the temperature of work also increases during when high strain rates are applied. Okay, because of this high strain rate, right? Now, when strain rate is increased beyond the usual metal working range, the elongation of fracture increases for many metals. Not all metals, but for most of the metals, especially aluminum and the high strength steels. Okay, once a critical strain rate is achieved. Okay, now when the strain rate increases, an interesting phenomenon is that the yield stress also increases, which is not desirable as far as forming is concerned. Okay, so this initially happens, but when a critical strain rate is reached, that is, initially the strain rate will start increasing, and at some particular point it reaches a critical strain rate. Once it reaches a critical strain rate, the ductility of the material drops sharply. Okay, and also it was observed that the strain rate dependence on strength increases uh, with increase in temperature. Okay, so this is what happens. As I said earlier, the very desirable property for a metal to form is actually a lower yield point and high ductility. Then only the material can be deformed properly, right? So here, when the strain rate was increased, beyond the usual metal working range. Okay, when the strain rate was increased, initially when the strain rate was increased, it was seen that the yield stress also increases. That is, the resistance to deformation also is increasing, right? Now, but when this strain rate was increased beyond a certain limit, that is, when it reaches a critical strain rate, strain rate, for most of the metals, it was observed that the ductility, the material property ductility, drops sharply, right? So which is desirable for forming. Okay, the ductility drops sharply, and because of which it can be formed, right? At the same time, the temperature was also found to increase, and the strain rate dependence on strength increases, right? Also the strength of the material also increases. Okay, now when the temperature increases, strain rate dependence on strength also increases, and hence the finally formed material strength also increases. Fine, I hope you got the point, right? Now, so now we'll see the stress strain effect on different materials, right? So as I said, it is not applicable for all the materials, but most of the materials obey this one. Okay, especially aluminum and aluminum alloys and high strength steels obey this condition. Okay, and these are the metals which are used for uh, most of the applications, like in aerospace and automobile industry, right? Now let us see what is the effect of this high velocity on particular metals, like starting with your mild steel. So in mild steel, the stress strain curve was obtained something like this. Okay. Now the first part, the 10 raised to minus 4, is actually for the conventional forming. The stress strain curve for conventional forming is shown by 10 raised to minus 4 per second. Okay. Now when it was increased to 500 per second, then the stress strain, the newly obtained stress strain curve, is something like this. Okay, so that means as the strain rate is increased, increased to 500 per second, 500 is a strain. per second when the strain rate was increased to 500, right, from 10 raised to minus 4. Okay, so it was seen that the yield stress increased considerably. You can see the yield stress somewhere here is increased considerably to somewhere here. Okay, at uh, but there is an interesting thing that yielding started at relatively lower value of percentage of strain. Okay, but the yielding is starting before that particular value of strain, right? Now the stress strain curve for copper, it is showing something like this. Okay, now the first one, 10 raised to 3 minus 3 per second, is for the conventional, and the second one, the 500 per second, is for the high speed one. Okay, now when the and it was shown, it was seen that there is an increase in yield stress is marginal. Okay, there is an increase in yield stress, whereas the yielding started at a considerable higher values of percentage of strain, unlike the mild steel. Okay, now when it was tested with aluminum, it was seen that the graph was obtained like this, right? And the first one, this 10 raised to minus 3 per second is for the conventional one, and 1300 strain rate, which is 1300 per second, is for the high speed one. Okay, now here there is a considerable increase in the yield stress as the strain rate is increased. Okay, you can see the value of yield stress is considerably increased from here to this point, right? So there is a considerable increase. Now as the increase in yield stress means increased yield strength and higher resistance to deformation at higher rates of strain with high velocity of loading. But this increase is marginal, corresponding to very high values of strain rate in most of the materials. Once a critical strain rate is achieved, the ductility drops sharply. So as we have seen earlier, now when aluminum was tested for high speed and for conventional one, your stress strain curve is found something like this, as we have already learned in our previous instructor materials and all, right? Now when the velocity was increased, so your stress strain curve was obtained something like this, and the observation here is that the yield stress increases for high velocity forming. Now it is not actually desirable, right? The increase in yield stress is not actually desirable for the process, right? Now the materials the yield stress increases. uh, okay, fine, the yield stress is found to increase, right? Now but this increase is actually for a it is actually immaterial, because when the strain rate is increased to the critical strain rate, as we have already spoken of, when this strain rate was increased to a critical strain rate, it reaches a critical strain rate, then what happens is the ductility drops sharply, and you can draw the material, or you may form the material, right? Now these are the stress strain relationship with different materials. Okay, now let us see the effect of deformation velocity. Now in high velocity forming process, velocity of deformation is much higher. See, the basic thing about this high velocity forming is, it is the velocity applied is very high, right? It is very high, right? Now when higher deformation velocities develop stress waves, we'll see what a stress wave is, which moves at high velocity within the material. The velocity of the stress wave is often closer to the velocity of sound. Moving dislocations during plastic deformation experience a damping force. The force is proportional to the dislocation velocity, except at velocities closer to the transverse sound waves. Okay, so when the velocity is almost the velocity that is developed is almost closer to the velocity of the sound. Okay, and because of this, the material deforms plastically. Okay, now the effect of material behavior. Okay, the microstructural changes introduced in this high velocity forming have much influence on terminal properties and the thermal response, as in the case of conventional metal forming process. The terminal strength of FCC metal is found to be higher after dynamic loading than static loading, but a reverse trend is observed in BCC and HCP metals, right? For the 10, it can be seen that for the terminal strength of FCC metals, you might know what an FCC metal is, right? Is found to be higher after dynamic loading, right? That means for a high velocity forming, the terminal strength, that is the final strength of FCC metal, when FCC metal was tested for high velocity forming, the terminal final strength obtained is found to be higher when it is compared with the conventional forming methods. Fine. Now, the effect of strain distribution. See, the important thing is that for a normal forming process, for the conventional forming process, there is a contact between the punch and the workpiece, and then it takes the shape of the die. Right. So there is actually a contact between the punch, and the punch is actually making a contact with the workpiece. But in the case of high velocity forming, there is no contact. There is no contact existing between the between the workpiece and the explosive material. Only the stress waves is coming in contact. Right. The for the stress distribution, sorry, the for the strain distribution in is almost uniform for the case of high velocity forming. Therefore, uh, because of this, you can produce many complex shapes without unnecessary strain in the material. Okay, now, so the first part, there is an effect of high velocity forming on the strength of material, or the effect of strain rate on the stress strain curve has been already completed. Now let us move on to the effect on stress waves and the deformation in solids. Now, to understand this, you should know what actually a stress wave is. Right. So let us try to learn in detail what a stress wave is. Okay, now in classical mechanics, or in the basic concept in strength of materials and all, when a body is acted upon by an external force, the whole body is assumed to be affected by the force immediately and moves with an acceleration as per the Newton's second law. I'll explain that. See, if suppose an external force is acting on this material, okay, you can see a block of material over here. If suppose an external force is acting on this one, as per the Newton's second law, we usually assume this as the even though the force is applied at this point, the force is distributed uniformly in the material. We'll assume that it as the force is distributed uniformly in the material, and if there is no barrier, this block moves as per the Newton's second law, which is F is equal to ma, mass into acceleration. That is, the block moves with an acceleration. The mass moves with an acceleration. Right. Now, actually, when the force is applied, no, actually speaking, when a force is applied at a particular point, the force is not actually distributed uniformly in the material. The force is actually getting concentrated at the point of application, and if you check with these two ends, this point you will feel the effect, and at the same time, at the farthest point here, there won't be much effect on the of the force. Right. Right. Now this can be explained by the concept of stress waves. Now this phenomenon can be explained with so you can see the effect is at this point. Okay, and because of this, the body is moving, right? And so this concept, or this actual scenario, can be explained with the concept of stress waves. And as per the stress waves, now due to the application of the concept of stress wave explains this phenomenon something like this. So when a load is applied at a point, stress waves are created at this point. Okay. Now this stress waves moves from particle to particle. Okay. So at this point, there will be a high intensity of the stress waves, and it moves to the farthest end, and finally, and because of which there won't be much effect at the other point. Right. So the loading occurred is carried from point of application to the other parts of the structure by stress waves. So simply the concept is the loading at a point is transferred to the other points by stress waves. Okay, now the stress waves are basically two types. One is your elastic stress waves, and the other one, if one is elastic, the other one will be, yes, you got it, and that is nothing but your plastic stress waves. Right. Now let us try to understand what an elastic stress wave is. Elastic waves act as the propagation of a disturbance through a material medium due to repeated periodic motion of the particle of the medium about their mean position. The disturbance being handed over from one particle to the next. The energy and momentum are propagated like this. The propagation is possible due to the property of the medium like elasticity and inertia. Okay, so an important point is that for an elastic wave, the particle always tends to come back to its original position as per the as we have defined an elastic material. Okay, so for an elastic wave, the particle always tend to come back to its original position. Okay, when the wave is set in motion, when set in wave motion. Okay, the propagation velocity of the waves depends upon the density and the elasticity of the medium. Okay, so elastic waves are simply those waves in which the particles always have a tendency to come back to its original position. Okay, and the energy and momentum propagates by motion of particles of medium, right? And this propagation is possible uh, due to the property of elasticity and inertia. Okay, now this elastic waves are classified into two types. Okay, and those are your longitudinal wave, or it is also called a P wave or primary wave or push or pull wave. Okay, so elastic waves, the first type is longitudinal wave, and the second one is transverse wave or S wave. Okay, we'll see what it is. Okay, so as we have already seen in strengthometry and all, when you apply a force, there is a force acting on the longitudinal, also the force acting on the transverse. To explain this concept, we are using this longitudinal wave and or P wave concept and the transverse wave or S wave concept. Okay, we'll see that. Now the longitudinal wave or P wave, P stands for primary or pressure or push pull. Fine. So P waves, uh, these waves are also called longitudinal waves or compression waves due to particle compression during their transport. P wave is transmitted from particle movement back and forth along the direction of propagation of wave. Okay, now this is actually responsible for the transverse effect. Okay, transverse loading effect, transverse stresses and all. This longitudinal wave is is responsible for that. Right. So nothing but it is a P wave is a primary wave which is acting along the longitudinal or the compression waves. Okay, which is acting on the longitudinal direction, and it is transmitted by particle movement back and forth. Okay, particle movement back and forth along the direction of propagation of wave. Okay, it moves back and forth along the direction of propagation of wave. Okay. Now, similarly, you can explain the concept of transverse wave or S wave. S wave, S stands for secondary or shear. Okay. First of all, we have P wave. It's a primary wave. S is the secondary wave or shear waves. So that means this is the wave which is moving in the transverse direction. Okay. One was moving along the longitudinal direction, and S wave will be moving along the transverse or the secondary or the shear direction or the transverse direction. Right. So the S wave stands for secondary or shear and is also known as transverse waves because particle motions are transverse to the direction of movement of the wavefront. Okay, so it is moving perpendicular to the longitudinal waves. Okay, so these waves involve shearing of the material as a wave pass through it. Okay, there is no volume change. So in short, you can explain these two as your longitudinal wave is uh, actually responsible for the normal stress, right? Now that it can be related with the normal stress. Okay, so it is the wave which is producing volume change. Volumetric change is produced by this longitudinal wave or P wave, whereas your S wave is responsible for the change of shape and it won't affect your the volume change. Okay, now as there is an elastic wave, we have seen that there is also a plastic wave. Okay, plastic waves or plastic deformation takes place in a ductile metal when the stress in the material exceeds the elastic limit. Under dynamic loading conditions, the resulting wave propagation can be decomposed into elastic and plastic regions. Okay, so under dynamic loading conditions, the resulting wave propagation can be decomposed into elastic and plastic. So once this once the deformation moves to the plastic region, the plastic waves effect can be seen. Right. So this is it, and this is the basic concept about the stress waves, and this is a very important topic. Right. You should be knowing the different types of elastic waves like the P wave and S wave. Okay, now because of these stress waves and all, there occurs the deformation in the material, right? In the materials. Now, I'm not going to the deformation area. That is the only area which I'm skipping because the deformation of metal area you might have already studied in your previous semesters. Like in, if I'm not wrong, you might have studied that in third semester The deformation, there are elastic deformation, plastic deformation, and the slip and twinning concept and all you might have already studied, right? If not, to get a better idea, I will share the link in the description below. Okay, so you may refer those animation videos and all in the description, and you may learn those topics. That is also very important. So don't skip those topics, learn it, and thank you one and all. Learn all those topics very well.